Hey, what's up, guys? Okay, so in this kind of this video that I want to talk about the very interesting complexity class called the interactive proofs. Oh, and this is a very famous topic, right? It's called IP. Okay, and I will like make some videos about I will keep making some video about this IP. Okay. Okay, so the before we say this, let's say some general story. Oh, by the way, if you want to see more complexity theory videos, that you can check out my video list below. Okay, so right, so you could imagine that this right. Suppose there's a mathematician, right? So or in a high school or whatever, right? If you want to prove something is true, then you will like write a proof. Right? You will write a proof and then send to someone, right? Send to someone here. And then someone will read the proof, right? So there will be some guy who should read the proof. Maybe it's your professor or it's your TA or whatever, right? So this will he or she will verify proof. And if he finds something is incorrect, then he will say it to you, and then you will try to write proof again. Maybe check some maybe there are some mistake, and then you modify it and you say it. And after you say it back, and then you say it after you say it back, and hopefully that this process will be terminated in a reasonable amount of time. Okay, so this idea basically is the interactive proof. Okay, so one famous result is in NP. Okay, so we know that they say L belongs to NP. Basically means that everybody knows it, but there's a Turing machine V, and for X belongs to L, there's a witness Y. So you have some witness. And the witness should be, let's say, X length is N, and the Y should be like bounded in poly N. So that VXY, right? So your verifier, this is called verifier, can easily check that the X indeed belongs to L, right? So we output 1. And if X do not belongs to L, then whatever Y, every Y you did, this verifier will always say no. Okay, so that means that you cannot cheat the verifier, right? If you write a wrong proof. Okay, and so one can like give this definition, right? One can like write the whole definition for this. So let me just write. So in this scenario, this interactive proof scenario, there are two person. One is the prover, and the one is the verifier. Okay, so idea is that the prover has you can imagine that prover is very powerful, right? This should be correct, right? Because I mean in the mathematics that the prover is so smart that he can come up with very intelligent proof, and the verifier just some editor or reviewer which review the proof. Okay, so we should say the effective or the correct definition for this interactive proof should be the following. Okay, so let's say fg to be some Boolean function. And then we say that the k-round interactive proof. By the way, this is the first this is the deterministic version. So we will like change this to be probabilistic version, but we first talk about deterministic version. Let's say on input x belongs to 0, 1 to the this. Let's call this fgx is a sequence. Is the sequence. Let's say 1 up to ak. Identify as follows. Okay, so first, the prover will send the A1 to the verifier. Okay, so prover has some function f, which prover will take x, right? And this may do something weird and A1 to the verifier. And when verifier get A1, the verifier will say, oh, so that I can take x and take a1. And the a3, the verifier and the prover will, oh, I get your a2. Then I can say, oh, I compute x, a1 and a2. And the verifier will say that, oh, I get your a3, so I can compute gx, a1, a2, a3. Okay, keep going. Okay, until that's 2i plus 1, that your f, x, a1 up to a2i, and then your a2i plus 2 will be f, so it will be g. So f is the prover can use. Prover as a function, or prover just f represent the prover, the what prover did, and the g represent what verifier did. Okay, so keep going. Okay. Okay, so this is the final 2 round. Okay, so usually there's a notation for final 2 round. This a2i plus 1, there's a notation called the out of fgx. Okay, so these guys are all the sequence, and the a2i plus 2 by definition I would say is called out f, and fg this is called g. So out of g fgx. Okay, this is the basically the notation of the proof, the interactive proof. Okay, so now we can write down definition. So this is called a deterministic proof system. This is called DIP. Okay, so this is called completeness. So need to satisfy the following. So completeness means that if x belongs L, then there will be a proof. This is non-trivial that in the mathematics maybe something is correct, but you cannot prove it, right? But there's a if something is correct, that you should be able to prove it. Also, there's a P, where is this interactive proof system that out of the verifier. So verifier will finally output say yes. So the final round of this verifier will give you 1. So verifier will say yes. Okay. And there's an idea called soundness. So soundness means that if x do not belong to L, then you cannot cheat. There's for all P, the verifier will output no. Basically, the verifier will output bullshit, right? Yes, doesn't means that your proof is doesn't make sense. Okay, and DIP also DIP requires the round K should be polynomial in it. So K should be this round. Should not like take forever. Okay. And okay, and usually yeah, that's it. And all these A1, A2, A3, all these are polynomial sites. And we are assuming that the prover, you can assume that prover is like so powerful, the prover can solve everything. Okay, so non-trivial theorem, where is DIP is equal to AP. Okay, so this is the proof. Okay, so let's prove the direction. Okay, so this means that in this kind of deterministic argument, that actually the whatever round doesn't make difference to be NP. Okay, so let's prove NP belongs to DIP. Okay, so proof is simple because right, so N because NP has 1 round proof. Okay, the reason is that let's say you're a prover, right? You're a prover, and this is verifier. And all you need to give an x belongs to L, right? You only just send the witness y. And the verifier just run vxy, right? Because by definition, there's a polynomial type Turing machine V such that the verifier can run vxy. And by definition, vxy will give you 1 if x belongs to L. And for every x being, if all x do not belong to L, right? Then whatever prover send into verifier, the verifier output no. Because This is also by definition, right? Okay, so this is a trivial proof. Okay, so non-trivial proof, maybe you need to think a little bit, is that the DIP is less than, is a subset of NP. Okay, so this requires maybe requires a little bit work or a little bit think. Let's imagine, is this correct or not? So right, so we need to find a witness. So what's the witness? So by definition, right, if you're a DIP, that means that you have this string, right? You have a string, so you have A1, A2, A3 up to like A of maybe up to AK, okay? And then this will causing the verifier to accept. Okay, so verifier will accept this. Okay, so we need to right. So this is witness. Okay, so we need to verify this is true, right? In the NP sense. Okay, so to verify it, so we just check where the verifier indeed produce this transcript, right? So we just check if verifier get exists, if verifier receive X, receive A1, and then where verifier get X and A1 and A2, give you A3, and then where finally this verifier accept 1. Finally this verifier output 1. Okay. Okay, so if X belongs to L, then such verifier exists. Right, such verifier behavior exists. Verifier behaves exists. Yeah, so it exists. Okay, so this means that, right, if X belongs to L, then I just provide you the witness, and then your NP machine just check, your NP algorithm just check all where verifier indeed produce this transcript. So this is your NP algorithm, right? Your NP algorithm just check the verifier, really verified. Okay, and then if X do not belongs to L, then that the node, so right, so if X do not belongs to L, then by definition, right? By definition, your for all other witness, right? There's no way to make this verifier accept, right? In the DIP. Okay, so it's the same proof. Okay, and by the way, in this kind of proof that if you check whether verifier indeed verify it, then you just fix the prover, right? Just saying the prover will send XA1 to be A2 and the XA1, A2, A3 to be A4. Okay, so basically finish the proof. Okay, so let me just say again, your NP algorithm will verify what verifier indeed do. Okay, so your NP just verify the verifier, and this can be checked in polynomial time. Okay, so the weird thing is that so this tells you that in order to make DIP stronger, so we need to add the probability. Okay, so we need to say that if X belongs to L, there is a probability verifier or the probability prover such that the final output of the verifier will output at least the probability verifier output 1 will be at least greater equal to 2/3. And on the other hand, if X do not belongs to L, then for all prover, whatever prover send the verifier will say no, right? The verifier will have the higher probability to say no. Okay, so this kind of probability will change this deterministic to famous interactive proof called IP. Okay, and in the computer science, that very large, very importance theorem is this IP is actually famous as a p-space. It's the same as p-space. Okay, this is in the future that hopefully I can make a video on it. See you guys next videos.